Okay, welcome to week 13. Can you believe that? Uh, of Violent Python. Oh, wrong display up. I teach 3 classes tonight, so let me bring the right briefing up for you. Okay. I had them all launched earlier. Now I seem to have closed the week 13 lecture. Okay, let's try again. Welcome everybody to week 13 of Violent Python. We're going to talk tonight about something you're all pretty much familiar with, right? MP3 files and how we can carve information out of the ID3 headers of MP3 files. Just a kind of a brief introduction to ID3 headers. I'm going to go into it in pretty much details. But if you have an MP3 player, or if you're playing MP3 music in your car and your car happens to have a video display or picture display, you notice that sometimes when you're playing a particular song, the artist or an image of the band and stuff like that will come up on the video, whether it's on your iPhone or your Android device or on an MP3 player or in your car. You can see that. You might be wondering where that information came from. And we're going to talk about that quite a bit tonight to go through that. But before we do that, I do want to go through last week's assignment kind of quickly, because I'm going to post the solution to that. But I want to actually walk through the NLTK solution that I came up with, which I've kind of been over several of the pieces of this, but I want to make sure that everybody got this. We had a pretty good session on Saturday during the Python tutoring session. And also on Monday, we kind of dove into a couple of elements that were related to that as well. Some really good questions came up. So let's actually start to walk through the ones that I didn't give you. In other words, I gave you the corpus length and the tokens found. Remember, the corpus length, when we look at that, is really basically the number of characters that were in the entire corpus, everything that was in those files that were in the corpus directory. The tokens are what we have come to know and love using the split method of strings and basically creating lists of words. In the vernacular of natural language toolkits and natural language, those are called tokens. And the reason they're called tokens is because they may not be complete words. They may be other strings. However, let's set a breakpoint here on each of the other items, the vocab size, each one of these that we didn't go over. And I'll kind of quickly walk through each one of those. So let me start the script, and then we can walk through those as we select them off the menu. Everybody can hear me okay and see my screen? Just, I like to ask just so I can remember to do that. Yeah, anybody? I should probably look at my chat window. Yeah, we're good to go, thanks. So I happen to have my corpus directory right underneath where my script is running. So I can just type /corpus, which is current directory, and the subdirectory is corpus. It's going to bring in these 4 parts of the trial transcripts that I brought in from the O.J. Simpson trial. And again, we can press 1, and it'll give us the number of characters, the total number of characters that were found in that corpus. We can press 2, and it's going to give us the tokens, which again are akin to words in kind of our vernacular. So now let's take a look at vocabulary size. So if I go to 3, we're going to set a breakpoint there, and we're going to calculate the vocabulary size. So remember, the vocabulary size, if I look at the text corpus here, basically you can tell that it's a list, right? It's all of the words or strings, if you prefer, tokens that were found within the entire corpus that we've downloaded, which was not huge, but it was pretty good size. So that gives us the number of those. So if I convert that into a set called vocabulary used, it'll eliminate the duplicates, right? We've done that before in converting lists to sets, since lists can have duplicates, but sets can't. And when I do that, I now have a vocabulary used variable that I created, and I can find what the length of that is, and I can print it out. And it says 6,564. So of those, let me say go again. So this will complete. I hit enter. So now we have a vocabulary size 6564. We had 153,000 tokens and 744,000 characters. So that gets us through the vocabulary size. So now we want to search for word occurrence. How do we actually do that? So if I say go, it's going to ask me to enter in a word that I want to search for. Now let's search for the word gun. And when I do that, it's going to basically make sure that you actually entered a word. You didn't enter a blank. And now it's going to use the text corpus that we created in the initialization of this class. This text corpus has lots of really cool functions in it. And one of those is count. So I can count the word that I just entered. It'll come back and tell me how many of those that it found. It found the word gun 6 times. Okay, so that's the second one. And we're going to go to the next one. Okay, keep going. Okay, the next one is a little bit more complicated. It's called concordance. So let's select concordance from my fancy menu here. And now it's going to ask us for a word that we want to concord. So let's say the word gun again, just so we have one that we know is in there. And it's going to try to compile the first 100 concordances of the word gun. What concordances are is, give me that word in the middle and give me 200 of those, 100 of those, and give me a string that's 200 characters in length and put the word gun in the middle, just so that I can kind of see what preceded it and what fell after it. So when I print that out, we get exactly what we expect. Here's the word gun that was in the center, and these are the sentences that preceded it, and these are the strings that preceded it and the strings that followed it. So if you're trying to get context of the word gun and where it was used in this particular transcript, you can find it. Now, you notice that there are 6 of these, not 100, because that's all it found, but that also corresponds to that we found gun 6 times before. So now the concordance actually matches. Let me say go, and certainly I'll certainly request input at the end here. Now let's take on similarities. This one tends to give people trouble because it's confusing as to what similarities mean. But again, the text corpus has a function called similar that we're going to use. Let me set a breakpoint here, and we'll say we'll give it a word like how about, let's pick a different word. Let's pick a word like evidence, or maybe proof might be a good word to use. So now I'm going to print the first 200 entries of the word proof that I'm looking for. And you notice when we print this out, you're saying, wait a minute, proof doesn't appear here. That's correct. What similarities are words that have similar meaning to the word proof. So if you kind of look at this, we see evidence and we see testimony, we see, let's say, discovery. So you're starting to find words that are similar to the word proof here. So what's the point of this? Why would we care about that? The reason we would care about that is if we were going out and doing a search like this, and we had a word that we wanted to search for, we may find similar words within the text, and then we can search on those to create a concordance, right? So this is kind of the investigative process. If I have a concept of some words that I'm looking for, I can look for those words, but then I can also find words that are similar to those and actually do that. Like you notice on this page, there was a word, I think I saw the word death here. So if I go ahead and continue my script and enter, just to kind of show you how this works, if I do 6 again, and I type in the word death, in this case, we're going to basically find words that are related to the word death in this particular thing. Sometimes they're not obvious that come up, but you find words like murder, right? That kind of corresponds to death. Let's see what else we see here that might be relevant to the word death. Okay, we have the word blood. We have the word, this one didn't deliver that much, but kind of think of it as kind of like a thesaurus lookup, with context. And that's what the purpose of similarity is. And we can kind of use that for a variety of purposes. The last one is that we're doing was the vocabulary. And the purpose behind this one was to determine the number of times a particular vocabulary word was used. So in this particular case, we're going to go through the larger set and we're going to use the vocab frequency items. So vocab frequency allows us to go to that text corpus and then get the vocabulary, right? That's one of the functions that are there. And now I can actually iterate through the vocab frequency items that I created. And for each one that I find, I'm going to add that frequency because it gives me that frequency for each one. So I'm going to add one of those rows to each one of those. And if I say F5, it's going to basically automatically tell me where we used to have to do this kind of manually in the past, but NLTK does it for me. And it gives me back the frequency of each of the words or strings. Remember, these are tokens that it found. So some of them are large. And the purpose of this is that if I'm looking through something and I have this idea that I want to search for something, right? But maybe I don't know. If I'm searching the entire corpus now and it will rank the words for me as their frequency, it maybe give me other words that I want to search for and perform a concordance on to get the context of where that word was used. One of the words that came up was Cato, right? And there was lots of entries that were related to Cato Kalin, right? So if I take that and I think this actually ran, right? Oops, I don't want to change my script. Why is that still there? Excuse me. So if I wanted to come back and do the concordance again, I could say 4, and I'm going to enter in a word here. And we'll enter in, no, steps over without saving. I didn't mean to do that. I can type in Cato. And now it's going to give me the concordance of Cato in my script. Once I say go again, these breakpoints are killing me. It occurred 113 times. And then I have that information. So that kind of gives you kind of an idea of, I must have searched for the occurrence of the word and not concordance. Let me run that one more time so I can do that properly. Let me clear all these breakpoints because they're causing me grief. So now it's going to show me all the places where the word Cato came up with. If you're not familiar with the O.J. Simpson trial, Cato Kalin was the gardener or whatever. So these are all the places that his name was used within the corpus that we're looking for. So now you have context. So again, this process of using the capabilities of NLTK to perform this kind of exploratory function gives us that ability. So any questions about how we're doing this, number one, number two, why we're doing this, and what value we could bring in just kind of introducing to you what some of the capabilities of NLTK will do for you when you perform those functions. Any questions? Any comments? Any thoughts?
Yes. Hi, Professor. Giselle here. I do have a question regarding the assignment because, and I'm not sure if I choose the wrong file, but in my assignment file, I was asking for the number 8, which it was to search for the index of the word, of a particular word that the user was going to enter. And so I'm wondering if that index meant the location of the word in the list, because that's what I did. Like, let's say, Los Angeles, and I enter LOS, the program was going to look for the first instance where they found that word.
Yep, that's correct. For some reason, I took 8 out. I don't remember why, but I did make a change last semester and I removed that from my solution script. And I can't remember the reason why, but what you're suggesting to do. So sometimes it's important to find the first location that a word is used within the context of the corpus. And that's what the index will do for you. It'll be,
Okay, that's what I did.
yep,
Yes.
that
Okay,
is correct.
perfect.
Yep.
Okay, thank you.
You're welcome. I don't remember why I removed it, but I did. I guess I didn't think it was valuable after the other things that were there, I guess. But good point. Any other questions? Any other comments? Can you guys kind of generally see the value of this? Or would you rather be looking at point and click tools that'll just give you the answer? I can tell you a little story and reason why this is important. In the Casey Anthony case, fairly famous case that happened, and it was a murder case where she killed her children. And the investigators that were looking for evidence on her computer couldn't find what they were looking for. They were looking for words like chloroform and so on and so forth, and they didn't find them. And one of the reasons they didn't find them is when she was using her Google and she was searching for them, she misspelled them. And so their direct search for words didn't return what they were looking for because their search was too specific. So in this particular case, when you're using and you have a corpus of data like that, that you can now search this way and look for word occurrence or look for similarities or look for generate concordances or the whole vocabulary. Now you can basically find tokens. Remember, they're not just words, they're tokens that you could identify and then go back and do more investigation. And it was a major flaw in that particular case that eventually got corrected. But in the initial case, as you might know, she was acquitted because they weren't able to provide some of that digital evidence. So we learned a lot of lessons from that particular case and why we use more advanced tools to do this kind of task search. Does that help a little bit to understand what we're trying to do here to give us a better idea of what we're looking for? Yes, no, maybe. Okay. All right, if there are no questions on that week's assignment, let's jump into something hopefully you'll have some fun with this week in the MP3 data carving. So again, as I mentioned earlier, we're all pretty familiar with this particular file type that we use to listen to music. And obviously there's many other forms of audio, but one of the most popular obviously is the MP3. So let's just go back to basics. What is MP3? It's an audio encoding format that employs lossy compression. So it compresses the audio portion of this, the actual music, to reduce the size with really minimal impact on the quality of the music that we listen to. The resulting MP3 content can be used to store files or to stream content over the internet. MP3 is more formally referred to as MPEG-1 and MPEG-2 audio layer 3, which means that it's actually part of the MPEG standard, which is the Motion Picture Expert Group that defines the standard for video and audio compression. That's the purpose of the MPEG group. These standards are the most utilized forms of video storage and transmission today that are out there. There are other forms, but this is certainly the most popular. And MP3 is part of that motion picture expert group that defines the standard for, remember, for compression of video and audio. So the structure of an MP3 file on the surface seems pretty simple, right? It consists of an audio format that has an ID3 header and then ID3 frames. We're going to talk about those in detail. Then it has the MP3 header and the MP3 data. So this is the MP3 data is where the actual song or voice that was recorded is. And it's compressed and compact in such a way that it makes it quite difficult to go in and manipulate that, because there are many, many different codecs that are used in the encoding of that particular data. So being able to manipulate that becomes quite difficult, and it's also relatively small. So each one of these little components, if you think of voice over IP, in other words, data that's being transmitted like we're using right now, this voice is being broken up into very, very small packets and transmitted via UDP in that form. And so there's not much data in each one of the frames. There are many different versions of the ID3 header, however, that contains a bunch of other information that is interesting to us. There was ID3 version 2, 2.3, 2.4, and the latest version is version 3 V2. And it's kind of currently the informal standard that is related to the ID3 header of MP3. So ID3 frames that are that first part of the MP3 file contains a plethora of information that might surprise you. Also, some of the frames, like APIC and COM and TLX and WXX and others, can be used over and over. In other words, you can create multiple entries of, for example, a pic. A pic is basically a frame that holds a picture. And there's no limit to the number of pictures that you can encode in an ID3 header. Really kind of useful. This provides kind of a huge opportunity to embed, hide, and communicate covertly using and embedding information in the ID3 frames. So let's take a look at these, and this is the part that might surprise you a little. These are all the different frame types that exist. I've highlighted a few that I want to kind of point out, but you can kind of see when you look at this of all of the different kinds of information that is stored here, the encryption, whether it's encrypted, whether one of the frames we talked about was a picture, the comment frame, those two can be duplicated. In other words, there can be multiple occurrences of those. Over here, we have a user-defined text information frame, and then we have even a user-defined URL, but there's also a whole set of URL links that can be placed into the ID3 frame. So hopefully your kind of mind is kind of going and saying, wait a minute, if I can embed a URL within an ID3 header, I could maybe use that to point to some command and control or some malware or something other than that that's not normally part of this music file. But there's other information here that's also very interesting that I should point out. Oops. If I look at play count, the play counter. So if I have this MP3 file, okay, and it has a play counter in the MP3 file within the ID3 header, if every time I play this, it's going to increment the counter. So let me ask you a question. If it does that, does the actual hash of the MP3 file stay the same, or does it change?
It will change every time.
It would change every time. Isn't that cool? So now I've got the situation where I can't basically create a hash to search for a specific MP3 file because it's going to be changed every time that file was played. Something that maybe people haven't thought of. It's like, wow, I can change the hash of the file every time this particular song is played. So just a plethora of information here, all kinds of stuff about the artist and the band and pictures and all of that kind of stuff. So what was the purpose of this? Why did they create this? They created this for the artists and for the publishers to be able to store content information within the MP3 file, and they went crazy and provided all of these places where I could store information within the MP3 file. Let me keep going. So this creates some vulnerabilities potentially. Like many data structures that we deal with, MP3 files have no real security built into them. Yeah, they have something called DRM, but it's a joke. There's really no security associated with it, not like Apple players where hardware is associated with it. You can play this file and everything. So there's really, the DRM is really there to basically dissuade you from copying the music, but there's nothing really to prevent you from doing it. So, except for Apple, that really enforces the digital rights management that's associated with that. Based on that, let's take a few things that we could potentially do here. Could we embed hidden text in the ID3 header? Sure, pretty easy to do, but maybe pretty simple to detect depending on how you went about it. Could we embed encrypted text or binary content? Yeah, still pretty easy to do, but detection may be a little bit more complex because we'd have to basically extract the encrypted content. Could I embed URLs that share, let's say, command and control information if I wanted to share that using a piece of music? Sure, pretty easy to do, maybe a little bit more complex to detect because we'd have to basically trace down all of those URLs. We know how many songs there are. We can embed data into existing or new images that we put into this MP3 file. Complexity of doing that might be moderate, and detection would be potentially more difficult unless I had the original. So exploiting the MP3 ID3 tags, this is a real offensive kind of capability. We can view the data fields in a hex editor, which is really kind of complicated and ugly. We can edit the fields. We can add or modify individual images that are contained within the ID3 header. We can hide the content in that image, and we can then splice modified images back into the MP3. In other words, I could use steganography or something to basically hide content in an image that already existed in the ID3 header, or I could add a new image to hide information in that. I can save the MP3 and it still shows the image, even if I modified it. I can upload this piece of music to a cloud player, right? Like Pandora, for example, and share with others. And now I can convey information. And you may think that doesn't work. Mike Rago and I demonstrated that at DEF CON 2 years ago, that we could actually hide information in images, put that information in an MP3 file, post it on Pandora, and download it and recover the data. There is no prevention of us or stopping us from doing that. And one of the reasons is there's no way to know whether this MP3 file has been altered. Everybody with me so far? Kind of cool? You guys still here?
Yep, still here.
Okay. Yeah, I like that. Kind of crazy. Yeah, maybe something, hopefully is something that you didn't know about and you kind of learned something new here. So a specific exploit, like I just described, I could take the ID3 APIC field that allows one or more images to be included in the ID3 header of any MP3 file. I can then take a current image or a modified image and hide malicious content in that image. I could create carriers for malicious URLs, command and control, all that kind of stuff, and even rat code, within that particular image, and then use cloud pairs for distribution. And that's exactly what Mike and I did during the talk at DEF CON a couple of years ago. So I've provided you with a script within a Python script that will extract this information for you. And I'm going to demonstrate that for you just in a minute. But basically what you can do with the MP3 file, the Python script, is you can basically process any standard MP3 file. And I've provided a couple of those for you. And then based on that, you can go ahead and perform operations on that using the script, which I'm going to demo for you, which will be certainly more interesting. And you can do this from the command line by just running Python, or you can do it from within Wing IDE, and I'll just do it tonight within Wing IDE. The one thing you haven't seen before, because we haven't done this, is in this particular case, the PyMP3 script requires a parameter. It requires the file that you want to process. We do that from the command line, and I'll show you how we do that. And then it provides some output. But let me do this from Wing IDE so we can get a better idea of how this actually works. So in this case, I'm going to go ahead and stop debugging the other script. I'm going to say go. And you notice that this little box always pops up when you actually run a script within within Wing IDE, but you've probably not used it before because you haven't had to pass a parameter. In this case, you need to pass a parameter, which is the name of the file. I'm just passing in EO, the letter O. It's the original .mp3 file that we started with. And I'm going to pass that name in. And the only reason I can do that is because EO.mp3 is in the same directory as my script. If it's in a different directory, you'll have to provide the full path to that. So if I say OK, and I'll just run this, don't save any file, it starts to process. The script will process this entire file. If I scroll back to the top, it provides some basic information. Again, all of this came from the ID3 header of the MP3 file, everything you just saw fly by the screen. And so in this particular case, it has the privacy frame, it has the soloist and whoever was the title of this, the orchestra, the early morning was the song. It was part of a jazz record. It was number 1 of 27 in the set. It was created in 2010, a bunch of information. Down here, you notice that we have 3 attached pictures that were associated with this particular MP3 ID3 header. Now, the rest of the file basically goes through every one of those frames and actually dumps all of the hex content of every one of those frames. So if you're interested, you can kind of come down here and look at the data that's included in each one of those frame types that we talked about earlier. Now, they all don't have to be present, but many of them are in this particular piece of music. So the other thing that happened, what my script does for you, is it extracts any of the pictures that were in there. So it carves them out of the MP3 file and actually places them in a directory. You can see that I've been working on a lot of stuff today. This is week 13, scripts, images, and it puts them in a file called images. So just to prove to you, I just did that. These are the timestamps on the file, which here on the East Coast, it's 7:30 p.m. So it basically extracted 3 files, EO, MP3-1, MP3.2, and MP3-3. I automatically named those for you, prefixing it with the name of the prefix of the MP3 file, and then I just numbered them because there's no information within the ID3 header as to what the name of those images are, so I named them. So we can view those images. So those are the 3 images that were included with this within this ID3 header, and I've extracted them for you. So now you have them. In addition, what you have is this header information, which showed you what was in the most important information for you guys are going to be this initial set of data that is in the MP3 file, which you're going to use on the subsequent image that you're going to analyze. And so, and it will also extract any images that were in that secondary file that I've provided you as well, which is es.mp3, meaning the stegoed version of the MP3. We've all kind of worked with steganography before. You're not going to have to do any least significant bit magic here. But there are going to be modifications in the second file. And your process this week, kind of fun, is you're going to use this tool as well as another tool that I put in D2L for you called JP Hide and Seek. It runs on Windows, that you need to use to extract the content that was in the images that I've hidden. Now, I could have added a file that has hidden information in it, or I could have modified any of the original ones that had with hidden information. And what I hid in those could be anything from simple text to another image to another MP3 file. I'm not going to tell you what it is, but it could be any of those things that I could have hidden there. So your challenge this week then is to use this program that's going to carve out that information. So let's go back to this week's assignment, just to kind of describe a little bit better of what you're going to be doing this week. This is week 13, of course. So your assignment is going to be, you have both EO MP3 and ES.mp3. You have the script. I think it has a slightly different name, but it's in the shell for you. And you're going to run the script on both the EO and ES.mp3 file. It's going to extract that information from the header of the ID3 header, and it's also going to extract the images. So there's going to be hidden content using steganography, using the program that I've already provided for you within the shell. That's going to have hidden information, but you need more information. The first thing you need to know is which images contained hidden content. You can do that by finding what images might have changed. What images might have changed from extracting them from EO MP3 versus ES MP3, or images that have been added. Once you can identify those, then you can apply the steganography program to extract the hidden content. But there's one more missing piece, and that is JP Hide and Seek requires that you provide a password. And what we wanted to do was to make sure that the password was provided to you within the header of the ID3 file that you're going to be looking for and extracting and using those passwords. And you're going to need to be able to see what's different in those first couple of pages of the output that comes from the script. Will basically allow you to find those missing passwords. And then what you're going to do is you're going to extract those. You're going to extract the hidden content. And then you're going to basically outline for your report, you're going to outline a step-by-step process that you went through kind of as a forensic examiner. Think about it from that point of view. And then you're going to provide the extracted hidden content recovered from the selected images, and then provide suggestions to improve the script. So it's a report that you're going to generate, but think about this from the point of view of if you were investigating this as a forensic examiner and trying to find the hidden content that was in the ID3 header, basically within the images of the that are contained within the ID3 header. There was a question from John. I don't believe that the talk was recorded, and the reason is that we presented it in Sky Talks at DEF CON, and Sky Talks are not recorded, unfortunately, because it's a closed environment. But good question. It might be floating around out there someplace. You could probably search for it and you might be able to find it. So any questions about what you're going to do this week? Hopefully this is kind of fun and kind of a relief. You don't have to write any code this week, but it'll kind of allow you to dive into an area where not many people think about where things are hidden. Questions? Comments?
When you process a file, will it create the images folder relative to the file you're processing, or relative to where the script is executing?
Yeah, where the script is executing, it'll put it in the images folder for you, and it'll name it so that you'll see, es.mp3.jpg or whatever will be in there. So you'll know the difference between the ones that came from EO, the original, and ones that came from the steg. So you'll have those once you run the script on those two files. You'll have all the images that you can then start to examine.
Perfect. Thanks.
Yep. Anything else?
Yes. So yeah, the entire lecture was really interesting. How we can utilize all the features of the MP3 to cover information. But so how do we actually insert images, for example, into those files? Is there any specific software that we need to use in order to do that?
Yeah, and I don't teach that part.
Yes, I understand. But yes, it was my question, right?
Yeah.
So it must be the different software that we could use to put that information in the MP3 file.
Yep, there are some commercial packages out there that will allow you to modify the ID3 header of an MP3 file, and the ones that I've used to do this, I developed myself. And I don't share that for obvious reasons. I don't want to turn you guys into hackers, but if you look on the internet, you will be able to find some programs out there that will allow you to manipulate the data in an ID3 header of an MP3 file. And the reason for that is you could be someone creating music, right? And if you're creating music, then you'd want to be able to fill in all of those fields, and you'd like to add pictures and all of that stuff. So there are definitely programs that are out there that will do that for you. I haven't seen anybody write something that will dump the contents of the ID3 and carve the stuff out like I've written here for you. But maybe somebody has. I have not seen that. It's the only program out there that I've seen to do that part of it. But obviously, if you're creating your own music, you can have a program that will allow you to, not necessarily for manipulation, but you could use it for manipulation in order to be able to modify your song.
Right. Okay. Well, thank you.
You're welcome. You're welcome. We have a hacker in the making. Good. Good thinking, because obviously there's some offensive capabilities here that can be used for good, obviously, and you know, by the good guys, let's say, in order to be able to use this this concept in order to be able to covertly communicate, for example. So just, you know, there is some, you know, positive uses of the offensive side of what we're talking about tonight. So that's why this is kind of the violent Python class. This is part of that. Hey, we can actually hide information. We've talked about STEG before, and now we're talking about how do we apply that in something other than an image by hiding information in another carrier.
Right. And I'm also wondering, you know, like, so that the entire usage of the ID3 might not be very well known, because I haven't actually read a lot about any cases where that has been exploited, like massively, for example. I'm in the defense and forensics track, so I'm always reading and trying to learn more about those things, but I haven't actually read anything about it. So it was really interesting when you mentioned it and you start to elaborate on, you know, how it can be exploited.
Yeah, no question. You know, I've been working in the field. I'm glad you brought that up. I've been working in the field of steganography for now 20 plus years. And, you know, early on, and maybe even today, when we talk to investigators about, you know, what their experience has been in the bad guys using steganography in order to be able to covertly communicate. And the answer typically, the first answer typically is, well, we're not seeing it. And my follow-up question is, well, are you looking? And then that kind of stops them in the track, and they go, what do you mean? I said, well, if you can't see it, if it's embedded in an image and you're not examining the image at that level, how are you're not seeing it because you're not looking for it? And then they go back, oh, wow.
Yes, that's right.
There are some cases we should go back and look at because we didn't find things we knew were there, but we never thought they would be hidden within images or audio files or videos and that kind of thing. So it's a great point that it's still today not something that investigators tend to take as seriously as maybe they could, especially as the criminals and worse become more sophisticated. Okay, anything else? I'm here if you want to talk about this more. Elizabeth, I know you're here and you've been through this yourself a couple of times. Any hints or suggestions that you can you want to convey to the students?
Let's see. So this is a really exciting assignment. I think this is probably one of my favorites that you teach in the whole course. I would say is to look at the header and compare the two different files when you run them with the program, so you can really see what the difference is, because that'll be a big help when you go to put in the username and password, and don't overcomplicate it too. I think that's a big thing students in the past have done, is when trying to figure out like the username and password, is they start kind of thinking of crazy username and passwords. But no, don't think of it too like don't think too much about it. And I'm trying to think what else.
I think
And
it's a good
also,
point.
yeah.
I think a good point that you're making is that also make sure that you document your steps. Remember, I'm asking you to kind of think about this from a forensic investigator point of view. So make sure that you document everything that you did so that you can include that within your report. And by doing that documentation, as what Elizabeth is saying, you can basically talk about the things that you discovered in the header that were different. Write those down, put those in your document. So then when you go to the other parts of the experiment where you're going to try to figure out what was hidden, you're going to have that information already documented in your report. I didn't mean to interrupt you, Elizabeth. You sounds like you had another point.
Oh no, that was a good point. That just added on to it. But yeah, no, that was basically it. Just to, yeah, I think documenting it as well also will just help you in the end when you go to submit your report for the assignment. So no, good points.
Okay. If there's not anything else, I'm going to give you some of your life back. So speak now, or we can talk on Saturday or Tuesday at the office hour if you have more questions. And I'll post this video tomorrow along with the solution to last week's assignment. So have fun with this, and we'll see you in a couple days. Have a great, if I don't see you, have a great weekend.
Thank you, you too.
Thanks a lot. Bye for now.
Bye.
Thank you.
Thanks, Allison. Bye-bye.